everyone, and welcome to the CP-31 solutions for 1600 rated problems. Today we'll be discussing the problem sending a sequence over a network. So let's just pull up the CP-31 sheet and open up the problem. And yeah, let's go ahead and read this problem. So we're given a sequence A which is sent over a network as follows. Uh, it's split into segments. Each segment of the sequence belongs exactly to one segment, and it is a group of consecutive elements of the sequence. Okay, and basically we're dividing A into some subarrays, right? So for example, this is A 1 2 3 1 2 3, and we split it as 1 plus 2 3 1 plus 2 3, right? So we split it into subarrays. Then for each segment, its length is written next to it, either to the left or to the right. Okay, and then this resulting sequence is sent over the network. So for example, this could have been sent as follows. We could have had the length, let's say 1 is here, so we could have its length over here or over here. Similarly, this one has a length 3, so the 3 could go over here or over here. Similarly, this one has a length 2, so it could go over here or over here, right? And there could be even different segmentations. So given a sequence B, is it a valid sequence B which was sent over the network? In other words, is there some sequence A such that if we send it, we would get the sequence B, right? And we just have to print yes or no answer. Yes if it was possible, and no if it is not possible. Okay. So as usual, the sum of n over all test cases does not exceed 2 times 10 power 5. So we know that it's a standardized question, right? So the expected time complexity, expected time complexity is roughly big O of n or big O of n log n. Okay. So let's dive right into the problem. The statement is pretty straightforward. So, okay. So basically we need to somehow figure out, right? Given, let's say, a raw sequence like 1, 1, 2, 3, 4, 5, 6, 7, 3, right? We need to figure out how to split this raw sequence into a way such that they form chunks. They'll form chunks, like for example, this chunk, such that one end of the chunk will have its length and the other will have its value, right? So for example, if we take this as our chunk, then we can say that the length 2, this chunk is length 2, and it has 2 values, right? Similarly, if we take this chunk, it has length 3 and it has 3 values. So that's what we're trying to figure out basically. Um, but we don't know whether it's going to get split to the left or to the right. Otherwise, obviously, our work would be pretty easy, right? So how do we go about this? One way you can consider this is, imagine we already made some chunks, right? Imagine we already made a bunch of chunks, right? We already made a bunch of chunks, and we want to figure out which one is the next chunk, right? So let's say this has some given like value x. Okay, so let's say this has some given value x. Now either the next chunk is of this length x, right? Either the next chunk is of this length x, or this chunk will continue until it reaches some position such that this whole thing forms a chunk, right? Until it reaches some position such that this whole thing forms a chunk, because this position will have the length so far, right? And then after this point, again, we can start looking for new chunks from this point onwards, right? But then if we have a greedy strategy like this, right? So this idea would be like some kind of greedy. If we have a greedy strategy like this to try and make chunks, we would have many choices. Okay, many choices at a given stage. At a stage. Okay. And the reason is simple. The reason is that, let's say we had a chunk like, for example, 1 1, and then we had 3 3, then we had 4 5 5 7 7 9 9. Okay. Now in this case, in a case like this, we can form multiple chunks. Okay, so one chunk which can be formed is like this with this 1 1, and then In another chunk which could be formed is, for example, this whole thing, right? So as you can see, it has length 3 and it has 3 elements, correct? Then similarly, we could have this one, and you can see it is length 5 and it has 5 elements, right? But we cannot obviously explore all these cases, because if we brute force this, it will be exponential complexity, right? Brute force, it could be exponential, or even if you try to lower it, it would be n squared. And if you don't brute force it, if you just take greedy, like you just take longest chunk each time or something like that, then that is also not guaranteed to solve your problem, right? So we can see that brute force fails because it's exponential time, and greedy fails because sometimes you might want longer chunks, sometimes you might want smaller chunks. So it's pretty hard to decide which chunk to take, right? So we'll have to look at it from another angle, right? So usually when greedy fails, brute force fails, we should have some ideas that we could use DP. So we should try to look at it from that angle, okay? So let us try to look at it from a DP point of view. What if we are in the middle of a DP state and how we can transition, right? So what we can say is, let's say this is our array B which we are processing, and let's say this whole part up to the position I. Okay, so this is position I. Up to this position I, this forms a valid chunk. Okay, this forms a valid chunk, right? So up to this position I, it forms a valid chunk. Now let's think about position I plus 1, right? So if this, let's say basically if this forms a valid chunk, then we can say that dp of I is equal to true, right? So now let's think about the position I plus 1. Okay, if you think about the position I plus 1, let's say it has some value x over here. So then if you add I plus 1 plus x, right? I plus x plus 1, and you get some value over here, right? And you get some value over here. Then basically that means, like, let's say this was 3, and then you have some numbers, let's say 3 numbers. So it means that this was 3 and this whole thing can also form another chunk, right? So that means that this whole thing also has some valid way to split it, right? So if this thing has some valid way to split it into segments, then this thing also has a valid way to split it in segments. So the key difference between this and our exponential brute force is, we don't care what the split is. We don't care what the split is, what split it is. We just know that it's yes or no, right? So we know it's yes, it is possible to split. So that's why we're saying that, okay, it should be possible to split for I plus x plus 1 as well, right? So we can basically say that dp of I plus x plus 1 is also equal to true, right? So if this is a valid chunk till here, then till here also will be valid chunk. Okay, till whole thing up till here. So let me just mark that in blue. So this whole thing can also be split into valid chunks. Okay, so that's what we have gotten so far. So this is for the chunks which start with their length, right? So if the length 3 is given in the start, then we are splitting in that way. What about the chunks which end at this length, right? So for that also we can do a DP. We just need to do a different type of DP. And what we can say is, so I want to know if this number is a valid end position of a chunk. Okay, valid end position of a chunk, right? If this is a valid end position of a chunk, so let's say there was the number 5 written over here, right? If the number 5 was written over here, that means 5 elements come here and the rest are again split into chunks, right? 5 elements come here and the rest are again split into chunks. So basically for this, what I need to do is, um, let me just remove this. So let's say we have I over here, I plus 1 over here, right? So here the value is, let's say 5, right? X equals 5. Then basically what I need to say is if I remove these 5 elements and form a chunk over here, is I minus X, right? Is I minus X this position? Um, so whatever element is over here, right? Has this formed a valid chunk? Has this formed a valid sequence of chunking? Basically, has this formed a series of chunks which are valid, right? So if this dp of I minus X is equal to true, then I can set dp of I plus 1 also as true, right? So basically we found two things, right? We found two things. So for every I plus 1, for every I plus 1, if dp of I minus X is equal to true, then dp of I plus 1 is equal to true, right? Also we found another thing, the other dp, if dp of I is equal to true, then dp of I plus 1 plus x is equal to true, right? So this is going to be our dp state and dp transitions. So our dp state basically says, does the prefix up to I, can it be split into valid chunks or not? And then we can do this transition. So what will be our final answer? Our final answer will be dp of n, right? If dp of n is equal to true, then our answer is yes. dp of n is equal to false, our answer is no. So pretty straightforward dp question, I think, especially for a 1600. But yeah, and also one more thing, what is the base case, right? Every dp must have a base case. So the base case is obviously dp of 0 equals true, because if you have 0 elements, then obviously you can split it into a chunk of size 0, right? So that's why if you just go through the logic, you'll see that obviously this position must be true, because if we form a new chunk here, it needs to see a true value in 0, right? So that's why we're setting dp of 0 as true. Okay, so this is our answer or final case, and this is our dp transition, right? So what is the time complexity of this? The time complexity of an algorithm is big. This dp algorithm, this we're just going through the numbers, it's big O of n, and the memory complexity is also big O of n, because we need to store the dp table, right? True, false values. Okay, so let's go ahead and have a look at the code, right? Here's the code, pretty short code. So we take n and we set create a dp vector. So initially all the values are false except dp of 0, which is set to true. Then for each number, we don't even need to store the numbers. We can just take the number in and basically the same thing. So here, since it's in terms of I and not I plus 1, right? Here I wrote in terms of I plus 1. Here it's in terms of I. So just subtract -1 in all of them. Okay, subtract -1 in all of them to understand the code. Okay, so we just need to subtract -1, so you'll understand the code. So this logic I've implemented here. So if dp I minus 1 is true, and we're also checking if I plus x is first of all valid or not. Otherwise, we'll have out of memory error, right? So we'll have out of bounds error. We're just checking the bound is correct. So if this is true and this is less than n, dp of I plus x is true. And if dp of I minus x minus 1, right? If I'm dp of I minus x minus 1 is true, this is also true. So I've written it in this way. If I minus x minus 1 is first greater than equal to 0, then dp of I can be equal to dp of I or dp of I minus x minus 1, right? So pretty straightforward. And the output is also simple. If dp of n, yes, otherwise. So that's all for this problem. Pretty straightforward dp problem. If you had some trouble coming up with this logic, then you should definitely practice some more dp problems, especially of these true false types, right? Yeah, so that's about it. The time complexity is big O of n, so pretty clean. Thank you for watching. If you didn't get any part, do rewatch it, right? Do work out the transitions by hand. Thank you, and see you in the next problem, in the next solution.